What we want to do next is to know how to add vectors, such as displacement, and we know that it has a magnitude and direction. And we also want to be able to do this to forces as well. And of course, being considered a vector, it has magnitude as well as direction. And finally, we also covered velocity, and likewise, it has a magnitude and direction. So because of this factor, that these quantities have directions, we can't treat them the same way as we do scalars. We have to treat them a different way. And that's what we're going to do next. So let's cover the triangle method first. Let's consider this to be vector 1, and we'll call it F1. And let's call this vector F2. So each of these vectors has a magnitude, the length, and direction. This is going in that direction, and it's at approximately at 45 degrees. And this vector is approximately maybe 50 degrees. So they have direction and magnitude, therefore they're considered to be vectors. So if I had wanted to add force vector 1 to force vector 2, the method that we do, let's add force 1 and force 2 together. In order to do that, what I can do is translate this force vector. As long as I keep it in that direction of 45 degrees, it's a valid translation. I can even actually move it this way, and that's still a valid translation of that force vector. So I'm going to put the head to the tail of force 2. And again, as long as I keep it at 50 degrees to the horizontal, I'm good. I can translate it. So just like that. So that would be force 1. And here's the head of force 1. And here's force 2. And here's the tail of it. So as long as I put the head and tail together, I can now determine the sum of those two vectors by drawing this triangle, which would be from tail of force 1 to the head of force 2. So let's call this force 3, and this is actually the total of F1 and F2. So let's now add force 2 and force 1 vectors together. So I'll need force 2 vector, and I can translate that. As long as I keep it at that 50 degrees direction, I'm good. So here's my force 2. And what I have to now do is take that tail and put it on this head of force 2. So again, I can translate it, and as long as I can keep it at that 45-degree angle, I'm good. So here we have the force 2 vector and the force 1 vector, and I have the head and the tail touching one another. And by drawing the final resultant vector of the two, I now have F3. So it turns out that regardless of how I add these two vectors, F1 plus F2, or the commutative version of it, which is F2 to F1, or F2 plus F1, we have the same vector F3. The magnitude are the same, and the directions are the same. Chapter 2, Section 2.3, this has to do with adding forces. What we want to do is be able to find components of a force that acts along some axis, and we're going to implement the parallelogram method. So consider this oil barrel, and let's say it has a mass of 100 kilograms, and it's being hoisted upwards. So there's perhaps a crane, and it's being hoisted upwards. So what we'd like to know is how much of this force acts along this link and this link. And in order to do that, what I'm going to do is idealize this situation by just looking at just this link right here, this ring. So I'll just draw the ring as just a particle where force F acts along it. And I draw a line parallel to the link right there. And I'll draw another line parallel. Make sure I get that correct. Like that. Right? So I now want to know how much of this force acts along the link that lies along these new axes. And I'm going to label these axes as U and V. Okay, as U and V. So to determine how much of this force acts along the links that lies on axis U and V, we use the parallelogram method. We draw a parallelogram such that it's parallel to the V axis, and we draw another side that's parallel to the U axis, and it is this force F along U and this force F along V that acts on these two linkages. So now what we would like to do is actually compute these forces, the force along the U-axis and force along the V-axis that is being acted upon the links AB and AC. In order to do that, we're going to use the law of sines, as well as sometimes we'll even need the law of cosines. So suppose this angle is given as A degrees. This angle right here is given as B degrees. And this angle we know from the problem statement, or we could measure it in the real life as C degrees. So using these information, we can find the magnitude of FV as well as the direction, and the magnitude of F sub U as well as its direction. So the law of sine is just a ratio of the sides to the angles. So for example, the ratio of this length F to the sine of this angle, so 981 newtons to the sine of B degrees, is equal to the length of F sub V, which we don't know, F sub V to this angle sine C. And it's also equal to F sub U, right? Because we have this force F sub U, which could be translated to be at this position. So F sub U, the angle opposite to that would be angle A. So it would be sine of A degrees. So with that, we should be able to write an expression for f sub v by using these two ratios. So f sub v would be 981 newtons times sine c degrees divided by sine of b degrees. If I had wanted to know the component of f sub u, I would use this ratio, and that would give me 981 newtons times sine of A degrees over sine of B degrees. So that is the way we determine the components of the force along a certain direction or axis due to a force being applied using the law of sines. Sometimes you'll have to use the law of cosines. So the law of cosine says if you're given some arbitrary triangle, and let's call this side B, side A, side B, side C, and opposite of side B, we'll call it the B angle. Opposite of the side C, we'll call it the C angle. And opposite of side A, we'll call it the A angle. Then the formula for the law of cosine is simply the length of the side is equal to the square root of a squared plus b squared minus 2ab cos of c degrees.